Plug-in hybrids have traditionally been defined by a balance between cost and efficiency. They typically use 400-volt architectures, sufficient for daily commuting, but often compromised in fast charging and high-performance scenarios. However, BYD's upcoming DM 6.0 platform attempts to shift this paradigm by introducing a 900-volt architecture, a specification usually reserved for high-end pure EVs, like the Porsche Taycan, into a mass-market hybrid system. While the specs, like 900 kilowatts charging and 3-second acceleration, are impressive, they raise a critical engineering question. Is applying such high-cost, high-complexity hardware to a hybrid vehicle a stroke of genius or a case of over-engineering? Hello everyone, welcome to Volt China EV. Subscribe to master the world's fastest-moving EV market before your competitors do. Today, we are conducting a technical audit of BYD's DM 6.0 platform. We will analyze the engineering logic behind the 900-volt system, the new Blade Battery 3.0, and objectively assess the pros and cons of this aggressive technological shift. Before we examine the architecture, a context note. Rapid technological jumps, like the move to 900-volt platforms, can significantly impact the residual value of older 400-volt vehicles. It accelerates technical obsolescence. I have analyzed these depreciation trends and identified which technologies are becoming the new industry standard in my 2025 Global EV Consumer Report. I cannot cover all the data charts in this video, so I've made the full PDF available for free download for a limited time. The link is in the description. I recommend taking a look to understand how these tech shifts affect long-term vehicle value. The core innovation of DM 6.0 is the full domain 900-volt architecture. Why move to 900 volts? The physics are straightforward. By increasing voltage, you can transmit the same amount of power with lower current. The report indicates that, compared to an 800-volt system, the 900-volt architecture improves power transmission capability by approximately 12.5%. Lower current significantly reduces heat generation, I²R losses, in the wiring harnesses and motor windings. This allows engineers to use thinner, lighter cables, reducing vehicle weight and copper usage. It theoretically improves the overall system efficiency, particularly during high-load scenarios like highway cruising or rapid acceleration. However, this transition is not without costs. A 900-volt system requires expensive silicon carbide, SiC, power electronics to handle the switching frequencies and thermal loads. It also demands higher-grade insulation for the motors and battery, increasing manufacturing complexity. The key question for BYD will be whether they can scale this cost-effectively enough for mainstream adoption. Moving to the propulsion system, DM 6.0 utilizes a 3-motor collaborative drive setup. This consists of an ISG generator, a front drive motor, and an optional rear motor, integrated via a planetary gear set. Technical capabilities. This layout allows for seamless switching between series mode, engine generating power, parallel mode, engine plus motors driving wheels, and a new direct drive mode. The system supports motor speeds exceeding 25,000 RPM, a significant jump from the previous 18,000 RPM standard. High RPMs allow for smaller, power-dense motors, 75 kilowatts per liter, without sacrificing output. Engineering concerns. While versatile, this architecture is mechanically complex. Unlike Tesla's approach of radical simplification, BYD is adding complexity to achieve efficiency. Managing the NVH, noise, vibration, and harshness of a 25,000 RPM motor and a planetary gear set requires extreme precision in manufacturing. Furthermore, the control logic required to smoothly synchronize 3 motors and an engine in milliseconds is substantial. While BYD claims seamless switching, real-world reliability will depend heavily on software calibration. The energy source for this system is the Blade Battery 3.0. The most notable change here is the shift in chemistry. BYD has adopted lithium manganese iron phosphate (LMFP). By adding manganese to the cathode, the voltage platform is raised, increasing energy density to 200 watt-hours per kilogram, roughly 10% higher than standard LFP. This helps close the gap with ternary lithium batteries while maintaining the safety profile of phosphates. To support 900-volt charging rates, up to 10 C peak, thermal management is critical. BYD uses refrigerant direct cooling, where AC refrigerant flows directly through the plates, improving heat transfer efficiency by a claimed 5 times compared to liquid glycol cooling. While LMFP offers higher density, it historically suffers from lower electrical conductivity and cycle life issues compared to pure LFP. BYD claims to have solved this with carbon nanotube conductive networks, but long-term degradation data for this specific chemistry in mass production will be a key metric to watch. The report highlights a peak charging power of 900 kilowatts, theoretically allowing a 300-kilometer range top-up in 5 minutes. This is achieved by utilizing the full 1,000 amps of the system. However, we must be objective about the utility of this feature. Currently, extremely few public charging stations globally can deliver 900 kilowatts or support 1,000 amps current. While the car is ready for the megawatt era, the grid is not. For most users today, the car will be limited by the station's output, not its own reception capability. While BYD's dual-gun charging solution helps mitigate this, the 900-volt capability is largely a future-proofing feature, rather than an immediate daily benefit for most drivers. Strategically, DM 6.0 represents a move towards tech equity, bringing high-end specs to mainstream vehicles. BYD aims to deploy this across its lineup, from luxury to mid-market. The risk here is cost. 900-volt components, SiC chips, and 25,000 RPM motors are expensive. Integrating them into lower-priced models could compress profit margins unless BYD's vertical integration can aggressively drive down component costs. Furthermore, as battery prices fall, pure EVs are becoming cheaper. Does a highly complex, high-maintenance hybrid powertrain still make sense if a pure EV with a 1,000-kilometer solid-state battery becomes affordable? BYD is betting that the engine safety net is still necessary for the next decade. BYD's DM 6.0 is undeniably a feat of engineering. It pushes the boundaries of what a hybrid powertrain can do, matching or exceeding pure EVs in performance and charging speed. So, what is my objective assessment? Technically, DM 6.0 is a masterpiece, but it may also be the peak of complexity. We are seeing a divergence in the industry. Tesla and others are simplifying, removing parts, moving to pure vision. BYD, with DM 6.0, is adding complexity, more motors, gears, higher voltages to achieve maximum efficiency. Is 900 volts necessary for a hybrid? For a performance car, yes. For a daily commuter, perhaps not. However, the real value of DM 6.0 might not be the peak numbers, but the efficiency gains. But consumers should be aware. Higher complexity often introduces higher long-term maintenance risks. As we move forward, the battle will be between integrated complexity, BYD, and radical simplicity, Tesla. DM 6.0 proves that the internal combustion engine has a role to play in the high-voltage future, but it demands a very sophisticated platform to stay relevant. Now, I want to hear from you. Do you think a 900-volt hybrid system is the perfect do-it-all solution, or is it too complex for its own good? Would you prefer a simpler pure EV, or this high-tech hybrid for your next car? Let me know your thoughts in the comments below. And remember, to understand the financial impact of these tech shifts on your next car purchase, make sure to download the 2025 Global EV Consumer Report from the link below. If you appreciate this objective, technical breakdown, please give this video a thumbs up. And remember, subscribe to master the world's fastest moving EV market before your competitors do. Thanks for watching, and I'll see you in the next one.